Evenings are your chance to forget the mistakes you made during the day. So, for the sweetest of dream, you can pave the way. Good evening to one and all present here. On behalf of PG and Research Department of Mathematics, DG Vaishnav College, I welcome all the PG students and CSIR aspirants. Prayer is the raising of one's mind and heart to God, or the requesting of good things from God. Now, Tamil Vaathu followed by college prayer.
நீராறும் கடலொடுத்த நிலமடந்து கெழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமி எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தளித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
சத்யவ்ரதம் சத்யபரம் த்ரிசத்யம் சத்யஸ்ய யோனிம் நிஹிதம் ச சத்யே சத்யஸ்ய சத்யம் ருதசத்யநேத்ரம் சத்யாத்மகம் த்வாம் சரணம் பிரபன்னாஹ. வாணி குணானுகதனே ஸ்ரவணோ கதாயாம் ஹஸ்தௌ ச கர்மசு மனஸ்தவ பாதயோர்நஹ ஸ்மிருத்யாம் சிரஸ்தவ நிவாச ஜகத் பிரணாமே திருஷ்டிஸ் சதாம் தர்சனேஸ்து பவத்தனூனாம். நமோ பகவதே தஸ்மை கிருஷ்ணாயாத்புத கர்மணே ரூபநாம விபேதேன ரூபநாம விபேதேன ஜகத் க்ரீடதி யோயதஹ. ஓம் சாந்தி சாந்தி சாந்தி.
This is C4 workshop, Chase, Crack, Conquer, CSIR Net, which will make the CSIR aspirants to go to the next level. Today, our resource person, Dr. C. Ilango, Associate Professor in Mathematical Sciences, Cardamom Planters Association College, Bodi Naikanur, Tamil Nadu. Now, I hand over the session to you, sir.
Good evening, my dear participants, research students. So far, your last 4 lectures, I gave you some important concepts and problem theory and problems solving techniques. Also, the relation between Poisson process, or Poisson distribution and binomial distribution, and normal distribution and binomial distribution, how that can be limited. Okay, all these things we are studying. And another important concept in the problem solving in probability theory is concerned in regarding Csir examination are concerned is conditional probability. How to solve problems using the technique of conditioning on the space, conditioning on the sample space. Okay, and with this, I would like to share something on conditional probabilities, and using conditional probabilities and sequence of random variables, we go for stochastic process. How a stochastic process becomes a Markov chains. Okay, and solving problems using Markov chains. Okay, with this, I would like to share some of the slides here. Okay, this is conditioning and independence. What do you mean by conditional probability? And if you know that the probability when omega is a sample space which contains all sample points of a random experiment and which have equal weight, same weight, they are equally likely. Okay, then what is probability of A? This is cardinality of A by cardinality of omega. That we already studied. And omega is a countable space, countable set. And each point omega, what do you mean omega? It's a sample point. So a sample point is a member which lies in omega. Okay. And we call actually P of omega, probability of omega means it is not a single point. Probability is a set function. Therefore, you call it as probability of omega is equal to probability of set omega, singleton omega. And how it can be calculated? Probability of A is nothing but you take all aggregate values of modulus of cardinality of A. So cardinality of A is, this is nothing but you count the probability of single elements, each elements, and take the sum of all these. Okay. Sum run over all elements in omega A, where A is a subset of omega, and divided by the total. So this is the original probability counting, okay, probability formula. And now let us come to the very simple thing, that is what is the probability of A given B? Where B is already an event that has already happened, okay. And what is the probability of A given B? That is equal to probability of A intersection B divided by probability of B. How it is computed? This is very simple. That is, when actually probability of A means, what is this? Cardinality of A divided by cardinality of B. So cardinality of probability of A given B means, here itself I can explain. A given B means B has already happened. So what we have to say about probability of A? That is, you are now, after conditioning on the space, now the omega, your total sample space, omega become a sample space. It is shrink to B because already B happened. Then what is the share of A in B? It is A intersection B. Therefore, cardinality of A intersection B divided by cardinality of B, because now your sample space is not omega, it is B. Therefore, that we have to calculate. And more secure, it is given. Now I would explain this. That is, if A is in S, it means that proportional weight of A in S. You take instead of A, what is the probability of A given S? What is the probability of A given S? That is A intersection S. Omega belongs to A intersection S. You take the total count divided by probability. So I can take probability, let S be omega. Your attention is from omega to S. The problem is, what is the conditional probability of A given S? S has already happened. So in some of the textbook it is given as B. A given B. Here I am taking as A given S. Okay, S is a smallest set, small event. That is a subset of omega. Therefore, probability of A given B is probability of A intersection S divided by probability of S. But provided the problem is, probability of omega is always positive. You know that. Here, probability of S should be positive. That condition should be there. Otherwise, suppose probability of A should be positive and it is finite. Okay, otherwise, suppose it becomes zero. What happens? Something by zero, it will become infinite. It cannot be dependent. Or 0 by 0, it cannot be dependent, indeterminate. Therefore, the condition probability of S greater than 0 is important. Now let us come to a very simple problem. All students on a certain college campus are polled as to their reaction to certain presidential candidates. there is a presidential candidate, and let D denote those who favor him. The candidates are favored by some students. So in a college, there is a college union election. For the union, there is a president candidate. For presidential candidate, how many people have voted? D. It's a set of students who voted in favor of him. And the student population, I call it as omega. And this has a classified so many races. You can say that it can be classified according to sex, age, and race. Okay. This sex according to X means male, female. And age means voting age, non-voting age. So above 18 and below 18. And race means, so it is a problem. It is black or white people. Black people or white people. It's a race. Black race is different and white race is different in European countries. That is in US. So we take this black. Now let us come to how you can partition this. If there are 3 different classes, the whole sample space can be divided into. This is very important thing because this kind of problem will be asked in the first paper also. Okay, first paper. Some of the probability papers questions can be asked from this kind of questions we expect. Okay, A, B, C. Then what do you mean by A complement? If A is female, what is the event of A complement? Male. B complement means white. C complement is non-voting age. C is voting age and C complement, non-voting. Therefore, this was said, omega is 40 is into 8 subdivisions. It is not 3. Something you think that it is 3 plus 3 is 6. It is not so. There are 8 possible. A, B, C. A, B, C means what? Female, black, voting age, above 18. And female, black, but non-voting age. And because they can favor the candidate, but their voting age may be not 18. Therefore, it has 18 has not attained. Therefore, it may be C complement is also there. Okay, and so on. Similarly, A, B complement C. A complement, B, C. You go on. Finally, what is the last one? A complement, B complement, C complement. That means male, white candidate, non-black candidate, person with non-voting age. So their respective numbers known in the complete poll is made. Okay, now let us come to the complement, the conditional problem. What is the probability of D given A complement BC? So you don't think that somebody this problem is probability A given yes. That's a very simple problem. So yes is a subset it is given. But here we are dividing the whole sample space into 3 different classes. And within the class, I am taking a particular class because there are 8 classes. I am taking the set. And what is the probability of favoring the candidate? Okay, presidential candidate, and who is already you have taken a sample that is subsample that is A complement B C. What is A complement? Means male with black non-voting age, and this is nothing but probability of A complement B C. D is also in the intersection. You take intersection, we take into. Okay, we can say that there is a standard A intersection B. We call it as A dot B, AB. Okay, for simplification purpose, notation simplification. And this is A complement B and this. Now let us come to the another one. What is the probability of not favoring the candidate? And but is female. Candidate is female and voting age. With voting age. That is A complement C, and this is A complement C intersection C dash. And this. So this is problem we can solve it very easily. And if you know the classification and the grouping principles clearly. Okay, now let us come to the next problem. A perfect die is thrown twice. A perfect die is thrown twice. So this here is the throwing twice is equivalent to throwing 2 dice simultaneously. Both are same because independently. They are independent experiments. Therefore, throwing a perfect die twice is equivalent to throwing a single die 2 times. Both are same. They give the same probability distribution and same sample space and everything. Okay, given that the total obtained is 7. So you take 2 dice, the total may be what are the outcomes? 1, 1, first one 1 and second one 1, 1, 1, 2, 1, 3, and finally it is 6, 6. Totally 36 cases are possible, and total obtained on the pieces, you take the total one, that is 7. How can you get to 7? 1, 6 or 2, 5 or 3, 4 and so on. Okay, that what is the probability that first point obtained is k, where 1 less than or equal to k less than 6. K is not a single k. It can be from 1 to 6 any number. First point, that is first die will appear on the first day, the number appear will be 1 to k. And the second die it can be anything. Okay, how it can be solved? Look at the list of example. Outcome of the total equal to 7, and there will be second diagonal, and their number is 6. Okay. Among that there is a case in, and the conditional, what is the conditional probability? Is equal to 1 by 6. That is total x plus, what is our yes now here? What is your restricted sample? X1 plus x2 is equal to 7. What is your original, what you actually look at the point, that is what is your favorable event, that is x1 is equal to k. X1 means, what is x1? X1 is the number shown on the first die. X2 is the number shown on the second die. Let x1, x2 respectively denote the point obtained in the first and second row. Okay. So your S is x1 plus x2 is 7. This is x1 is equal to k. Now you look at the probabilities. The probability that x1 is equal to k given x1 plus x2 is equal to 7. That is this one. This is intersection. X1 is equal to k and x1 plus x is equal to say divided by this. The probability is 1 by 6. How you got it? X1 plus 7 is means 1, 6. What are the possibilities? Now, if you look at the possibilities, it is 1, 6, 2, 5, and 3, 4, 4, 3, then 5, 2, 6, 1. So the possibilities is 6. Then x1 is equal to k. K may be anything from 0 to 1. Okay, this is only 1 point. Okay, it is 1 by 6. The fact that this is true for every, it is the fact that this turns out to be the same as unconditional probability. Now look at the beauty of the problem, that is, what is your, when you are throwing 1 die or 2 dice, what is the probability of getting number 1 to 6 on a single throw? It is 1 by 6. But here also we are getting, you are throwing 2 dice and also condition, you are giving a condition that the total number should be 7. Here also it is, that is an accident. This is not only, it is an accident, that is a lucky choice of 7. Number you have selected number 7, therefore it is 6. What are how many possibilities? Suppose instead of 7, you select 8, you cannot get this possibility. Therefore, then your choice of the number 7 in the subsampling is very important. That is why you got this answer. It is not, in general, it is not true. It is only the value of the total allows 6 possibilities. X equal to k, when x equal to 6, it is 1 by 5. You look at this, x1 plus x2 equal to 6, the value is 1 by 5. If x1 plus x2 is 9, if the total is 9, total on the 2 faces is 9, the probability is 1 by 4. 1 by 4 for this one, 3 to 6. Here it should be obvious what is conditional probabilities. Now let us come to the important point, that conditional probabilities. And now let us ask some simple questions. Suppose x1 is equal to 4. What is the probability that x2 is equal to k? So you are fixing x1 and varying x2. What is this? That is conditional probability of x2 is equal to k given x1 is equal to 4. This is also a it is also the conditional probability, just like x2 is equal to k. You look at this, x2 equal to k, given x1 equal to 1, that is x1 is equal to 4. You just apply your formula, x1 and x, and this is x1 equal to 4. And this applying formula, probability A into S divided by probability of S, this is 1 by 36. There are 36 possibilities are there. You are fixing 4, and here k. So what is the probability of this? 1 by 36. Because 36 cases, there is only one case is there. Okay. And come on, one k may be anything. Okay, we have taken k is any x equal to k, it's from 0 to 1. Therefore, it is 1 by 6. The answer is. Now look at this. You take the reverse case. Suppose you fix x1, first one is 7, but you have to get the sum is 7. First one is always 4, and sum should be 7. What is the possibility? Only one possibility, that is 3. x1 plus x2 should be 3. There is no other possibility there, and therefore 1 divided by this probability x1 1 by 6, and you get. Okay, so all these things. In future, I am going to give you a very simple thing in random walk. This is an example of what is random walk. Suppose a person at street is there, a drunkard person is walking along a street. How he will walk? It is not a straight. He may go up and go down. It is called a random walk. Usually a sensible man cannot walk random. His walk should be straight. Okay, because he has an objective to reach a goal, and his walk should be always towards that, whether it is vertical or horizontal, whatever it may be, or cross. Whereas a person who is drunk, he has no sense of brain, and that should be a random walk. And that is the best example for Markov chain. We are going to do the stochastic process that I will show in my next part of lecture, and that is stochastic process. A particular kind of stochastic process is called Markov process. This Markov process is very simple one. The future state of the system depends only on the present. When continuously you are taking a random variable, x1, x2, a sequence of random variables, that is x1, x2, etc. That is xn plus 1. Okay. Xn denote the nth state of the random variable. Xn plus 1 gives the n plus 1 state of the random variable. That is, n plus 1 state depends only on the nth state, not on the previous state. Then it is called a Markov chain. So that is also a random chain. That is, if you take a drunkard person, his nth step depend only on the n plus 1 step depend only on the nth step. Okay, that is why it is a Markov. Now let us come to the next problem. Consider the waiting time. This is waiting time distribution is a very important distribution. This is always an exponential distribution. As I told you in the earlier classes, if there is a queue, people are arriving according to some process. It's a Poisson process. So we can count the number of successors. The number of successors are probability x equal to x is e power minus lambda into lambda power x by x factor. Okay, that is lambda is a parameter. And the interval between two successive persons to a queue. Interval, you look at that, that is always an exponential distribution. That is why there is a close relation between exponential distribution and Poisson distribution. And this is called waiting time. What do you mean by waiting time for a particular event, success? Suppose first person comes at 6 p.m. and second person to the queue comes to 6:25, 25 minutes. Third person may come quickly, that is 5 minutes. So the arrival waiting time for the success is always exponential. For a bias coin, consider the waiting time x. For a bias coin, suppose bias, it is not uniformly, it is not regularly distributed. Knowing that, it has fallen tails 3 times. You look at this, you are continually tossing a coin. This tail fallen 3 times. What is the probability that it will fall heads within the next 2 trials? Okay, now you are throwing in fall 3 times. It is 3 times tail has occurred. Now what is the probability that next 2 trials head will fall within next 2 trials? So we have to wait for 2 trials. Okay, so waiting time is 2 trials. How we can do that? Now let us take probability of conditional probability, that is x is greater than or equal to 4. What is x? Waiting time. We are waiting for 3 times it first time we waited, that is first time, and second time. Therefore, it is x is greater than or equal to 4, and that x is less than or equal to 5. Within next 5 trials, we have to get a success. Waiting time is less than or equal to x. What is the probability? That is probability x greater than or equal to 4, and this you take the intersection of these two. It's x greater than or equal to 4, intersection x less than or equal to 4. What is that? That is nothing but the interval x lies between 4 and 5. Okay. And now let us. So this problem is very simple. Now let us come to the next part. Probability x is equal to n. What is probability x equal to n? That is q power n minus 1 into p. That is the number of, this means we have to waiting for a success p. So after how many times you will get, you have to get the success only at the nth task. You have to get the success at nth task. Therefore, how many times you get fails? N minus 1 times. So q power n minus 1 into p. Where n is 1. You able to understand my point? That is, our waiting time for the success is n. That means at the nth trial only I can get a success. What is the probability of success? P. So how many times I got failure? N minus 1. So q into first time q, failure. Second time q. N minus q into q, n minus 1 times q power n minus 1 into p. Okay. Therefore, now you look at this. What is the probability of x greater than? Here you have to calculate this one. Probability x greater than or equal to 4. And probability x lies between 4 and 5. 4 and 5 means it is 4 and 5. There are two ones. This is discrete variable. 4 means, here time means time is not a continuous, because you are throwing first time, second time, third time. So time is not a clock time. Here time means counting the number of trials. Okay. Now look at how many, what is the probability that x greater than or equal to 4? You have to wait more than 4 times. That is sigma n. N varies from greater than or equal to 4 means what? It starts from n to infinite number of trials. So I can get success only after 4 trials, and it will go up to infinite. Then what is the probability of success? Q power n minus 1 into p. That is equal to q power n. Our n is 3. Therefore, you have to put q power 3 p power 1. This means 3 times failure and 1 time success divided by 1 minus. You add all these things, you will get q power. This is 1 minus q, and q by 1 minus q. So this you put the, you get the summation of this, that will give this answer. That is equal to q, because 1 minus q is p. P and p will cancel. It is q square. How do we sum the series? That is very simple. You take, how can you sum the series? This is nothing but a geometrical series. Okay, you take p outside, q power n minus 1. Put n equal to, but n minus 1 is equal to k, and you adjust this term according to this. Then you apply your geometrical distribution. Again, from 5.1.7, what is the probability of 5 x lies between these two? That is, this is very simple, because you have to 4 probability of x equal to 4 and plus probability of x equal to 5. Okay, 4, you will get success at the 4th trial. That means QQP. Here, success occurs at the 5th trial. Q4. So this is that. And that's, you now look at the, you divide it. This divided by this will give you this answer. P plus QP. This is the probability of success. Now what is the, now we will come to our original problem, that is 5.3. What is the probability of coin falls head? That is probability of 1 less than or equal to x less than or equal to, that is P plus QP. Probability of getting at least once in 2 trials. So head occurs at least in 2 trials, that is your P plus QP. Now let us come to the next problem. we shall bring out an analogy between geometrical distribution. What is meant by geometrical distribution? That I have told you that it's success Q power n. This is nothing but a geometrical distribution. That is waiting time distribution. How many trials you need to get a first success, and this is a geometrical distribution. Okay, and this geometrical distribution is very much important, and this geometrical distribution gives rise to binomial distribution. Okay, there is a interrelation between Poisson distribution is interlocked with exponential distribution. Similarly, binomial distribution and geometrical distribution has a closer link. Whenever you count the number of successes in binomial sense and the interval between two different successes in the binomial process is nothing but a geometrical distribution. So that is why this is given probability x greater than or equal to q power n. And you can look at this conditional probability x greater than n plus 1, x is nothing but x greater than n plus m divided by x. Because you take the intersection of this x greater than m, that intersection is same. Therefore, and here it is q power m plus n, because x greater than n is q power n. And this is that. What's the meaning of this? Your waiting time for the success is greater than n means n times greater than n means your success may be at n plus 1 only. Therefore, how much time you will be failure? N times failure, q into n times, that is q power. Here it is q power n by n plus. It is memberless property. So you don't worry about this x is greater than m or not. This is immaterial. Therefore, it is you get q power n, and therefore we can say that it is memberless property. And you don't look at what is n or something. How much time you have taken n, you don't worry. You worry only about m greater than n. That is why it is. And the same thing we acquire in the memberless property in waiting time. That is continuous waiting time. You look at this. T is an event. T is greater than s. Okay. Let T denote the waiting time in an exponential distribution. Okay, waiting time in an exponential distribution for the next success. Okay. Then we have analogy, that is, what is the probability T greater than S plus T, given T is greater than S. Already time is greater than S. What is the probability that it will occur after S plus T? That means it will you forget about S. You take only T. That is what is the probability that T is greater than T. That is clear. Okay, because this you can forget. This memberless property leads to the Markov chain. That is why Markov chain is future state depends only on the present state, not on the past. We are forgetting the past. How much time it has passed, you don't worry. That is why I told an example of fishing. Okay, a person is waiting to fish, we're waiting in a fish pond to catch a fish from 6 o'clock. But another man who is come by a car at 9 o'clock and he is getting a fish. His waiting is useless. A person who is waiting from 6 o'clock is useless, but the success goes to them. So that is why your previous waiting is memberless. You look at this probability of T greater than, you take the intersection of these 2 points, intersection S plus T, this is nothing but T greater than S plus T, divided by this. What is the distribution of this for this exponential distribution? It is e power minus lambda into S plus T. Okay. Here, according to exponential distribution, probability T greater than S is e power minus lambda S. Now you cancel, you divide these two, you will get e power minus lambda T. Therefore, S gone. S is strike out. And this is probability T greater than T. And this is memberless property of. And this leads to Markov process that I will do. Okay. With this, we can solve so many problems. Now let us look at only one problem, and then we can go to the next. Consider all families with 2 children and assume that boys and girls are equally likely. Consider our families with 2 children and assume that boys and girls are equally likely. So we are treating boys and girls. That's a sample space may be denoted schematically a 4-point boy, boy. Okay, you take 2 children family, both of them will be boy, and boy, girl, girl, boy, and this one. B equal to boy, and I go. And 4 points have the probability. Now, what is the probability of getting a boy? 1 by 4. Boy, girl, that is also 1 by 4. And maybe therefore 4 n points. Where n is, so if you take a very large sample, okay, and how many points you get? That is 4n. And now look at that. If a family is chosen random from omega, from this, I'm selecting a family from random and found they have a boy in it. And what is the probability? It has another boy. That is BB. The answer is 1 by 2. The answer is 1 by 2 because it is nothing but how many BBs are there? The boys is concerned, there is only 3. And out of this, we are taking omega is found a boy in it. Therefore, the possibility is only these 3. And from that, what is your boy? And that is what the quick answer is 1 by 2. If you dumped in the conclusion, they equally like 2 sexes, but it is a mistake. Why? Because there is a relative frequency. Now look at this. A is omega. There is a boy in omega. There is a boy in omega. Okay. B equal to omega if there is 2 boys in omega. This omega is a sample point. Your sample point should contains only 1 boy here. And here, but usually you think that if there is a boy and this boy is our concern, therefore boy and girl are there, and you are getting boy. It is quickly people, when you go to examination, competitive examination, you come to the conclusion that it is 1 by 2, but it is not so. It is 1 by 3. Why? But if you look into the sample space clearly, you can do it because only 3 possible boy is occurred in the 3 cases, and only 1 case is boy, therefore 1 by 3. But schematically, when you come to this, and if B is contained in A, our B event is contained in A. Very clear? Because within A, there is a boy. So it may be 2 boy also. Our B is also a member of this. Therefore, A intersection B is B. Now the question is probability of getting 2 boys given A. A is a boy in B. Therefore, probability of B by A. This is 1 by 4 by 3 by 4. It is okay. Okay, now let us come to now I am going to explain, I will go to the next important topic, that is I introduce the random sampling, conditional probability, how to do conditional probability, what are the uses of conditional probability, and because I am going to introduce you a new concept that is called Markov chain. That is a stochastic process. What do you mean by stochastic process? It is nothing but a family of random variables. This may be discrete with over the time. Over the time you observe, you get xn, n equal to 1, 2, 3, or xt, where t varies from 0 to infinity. And now let us look at the next slide. Markov chains. So first I am going to take a family of random variables with discrete time. So if you take a stochastic process, there are 2 kinds of spaces. One is state space, other one is time space. With xn, I am taking n equal to 0, x0, x1, x2. These are family of random variables. And x0, what is x0? X0 is the initial state of the system. And x1 denote the first state of the system, and the x2 denote the second state of the system, and the x3 third, and xn is the nth state of the system. For example, I can give a very simple example. Suppose you are running a shop, TV shop, and that xn denote the number of TVs in your shop on the end of the nth day. You are starting with the 0th day. Okay, at January 1 is a 0 day. January 1, 2021 is the 0 day. You count it. Okay, you started counting your process. Let xn denote the number of items, TVs in stock. Okay, number of TVs in your shop on the end of the nth day. So when you close the shop, you take the stock. Okay, how much TVs are there on the nth day, end of the nth day, and that is, we call it as Xn. And then X0, X1, X2, X3 denote and stochastic process. Very clear? And I can take the let Xn, in a queuing system, you consider the queue. And Xn denotes the number of people in the system. Okay, when the nth customer leaves, okay, there is a queuing system, a server is there, a single server. You look at the very simple MM1 queue. Okay, only one server is there, and people are waiting for service. And let Xn denote the number of people in the system when the nth customer leaves the system. So after getting the service, nth customer leaving, then he look back the queuing system, how many people are waiting, and that is Xn. So that is called stochastic process. Now that stochastic process is always, I can give these two examples I told you. One is stock inventory problem. Another one is queuing system. Both are Markov chains. We can apply Markov properties because the future state depends only on the present state. First I come to the first one. Okay, probability that in the end, I told that Xn denotes the number of items in the stock when on the end of the nth day. Okay, what is actually probability Xn plus 1? Xn plus 1, n plus 1th day stock is depending on the nth day stock minus the demand on that day. Okay, you have to remove the item that was sold plus how many items you get from your distributor on that day. Okay, that all these things are fixed there. Therefore, if Xn is known, all other things are, it is fixed. How many items sold, that you know, and how many items you bought from your distributor, that you know. Therefore, Xn plus 1 depends only on the Xn and the previous Xn plus 1 day stock, Xn minus 2 day stock, and X1 day stock, X2, and first day, and all these things are not necessary. These are not considered. Why? Because all that other informations are imbibed in the nth state. That all that things are, this is memoryless property. Okay, if this memoryless property is there, then we can say that it is a Markov chain. Now let us look at the general definition. A discrete time process Xn n equal to 0, 1, 2, 3 with the discrete state space Xn. But the state space is also Xn. Xn, I told you that the Xn denotes the number of people in number of item in stock when on the end of the day. Okay, nth day. It may be 0, no TV, or only one TV or two TV. Now look at the queuing system. Xn denote the number of people in the queue when the nth customer leaves the system. Therefore, Xn may be 0. There may be no customer in the system. Okay, because he may be the last person to get service, and after that, when you look back, there is no person in the system. The server will take the rest. Okay, now let us come to the one. It may be only one person or two persons. So this is a discrete. The state space is discrete. Here the time space is also discrete. So this is a stochastic process with the state space is discrete and time space is also discrete. Now, I would like to give a classification of stochastic process also. Stochastic process is concerned, there are two important things. One is state space and another one is time space. The state space may be discrete or continuous. The time space also discrete or continuous. So here we are taking both are discrete. Time space. Now suppose instead of take xt, where xt denote number of, I put xt where t belongs to 0, infinity, interval 0, infinity. Here I put xt, t belongs to 0, infinity. Then what happens? Xt denote the number of, I define random variable in a different way. Xt denote number of items in stock at time t. At any time I enter the shop and look at how many people. Evening, it may not be at a particular time. Okay, at the end of the day, it may be at any time, clock time. Morning 6 o'clock at 6 hours 2 minutes or 7 hours 15 minutes. At any time, it is a continuous variable, 0 to infinite. At any time, I can enter xt denote the number of items in stock at time t. That is here the sample space, the state space is discrete. State space is discrete, but time space is continuous. Clock time. Okay, now look at another thing. What is suppose state space is continuous. When the state space is continuous, let xn denote the price of gold on the end of the nth day. Today is end of the nth day means the sale closes at 10 a.m. 10 a.m. the account is closed. The interest level, what is the gold price? That xn denotes price of the gold on the nth day, end of the nth day. That is, the gold price may be 3,750 per gram. It is 4,750 rupees, 70 paise. It is continuous. Whereas n is your discrete day, first day, second day, and third. Now look at another one, xt. Let xt denote the price of the gold at time t. It is the case in which both state space and time space are continuous. Okay, therefore, there are four important classifications. State space is discrete, time space is discrete. State space is discrete, time is continuous. State space is continuous, time is discrete. And it is continuous, that is also continuous. Therefore, there are four classifications. With this, now let us come to your Markov chain. A discrete time stochastic process, xn, with the discrete state space is a Markov chain with the Markov property that I told you. In the n plus 1 state, xn plus 1 equal to j given. That is conditional probability. That is why I introduced conditional probability earlier. Xn is equal to ax with all these. The initial, the state is I0. The second x1, it is I1. And in the n minus 1 trial, it is In minus 1. And n minus 1 state, it is n minus 1. In the nth day, it is I. How many TVs are there? On the nth day, I TVs are there. N minus 1, In minus 1. This is equal to probability that xn plus 1 xn. And all these things are removed. These are useless. Okay, we are disregarded. You disregard all these previous states of the system, and this is equal to this probability. The conditional probability of these two are equal. This is not equal in all the cases. There are some specific cases, that's why I told you the inventory and queuing system, these two are equal. Other systems are not equal. Therefore, there you cannot apply your Markov chain principle. If this condition satisfied only, it is called a Markov chain. Then you can, using this, you can solve the problems. Sometimes people do ambitious things, and there are some problems in which it is the original Markov chain, the stochastic process, they consider need not be a Markov, satisfy Markov property. But so they assume that it is Markov process and solve the problem. Finally, you get a wrong result. Okay. Sometimes there is another problem. There are some problems. The n plus 1 state depends xn and xn minus 1. It is double. And we can call it is doubly Markov chain. Okay. Double chain Markov chain. That is two state. It depends on xn plus 1 depending on xn and x minus 1, but not on the others. So that kind of problems are also there, but that are very meager. Okay, now let us come to this point. In other words, what is actually this means? Past conditionally independent of the future. That is, given the present state, the past contains no additional information. If you given the present state of the system or stochastic system or your random process, in the random process of your observation, given the present state is already known, the past has no value, and thus we can say that it is a Markov chain. The Markov property is a probability model because by assumption, one supposes that the important variables for the system being models are being included in the state space. So important features are included in the state space. If you are looking at the value of the state space, you have to solve all the problems. Okay. Now we consider another important thing, homogeneous Markov process. What do you mean by homogeneous Markov process? This is something different. That is, in some cases, n state, n plus 1 state depending upon n. These two are, but this probability not equal to 0 and 1. So this is also one step. This is also one step probability. If the conditional probability, one-step conditional probabilities, all the probabilities are equal, it does not depending upon the time. It does not depending on the time. We can say that it is time homogeneous. Actually, it is called time homogeneous, but it is given here. It is It is time homogeneous. It is not mentioned here, but actually because it is independent of time. If the Markov property is independent of time, we can say that it is homogeneous. Actually, in some cases, this x equal to j depending upon time. This random variable, if you write this is Pij. In a general notation, Pn plus 1i equal to this, we call it as Pij. Pijn. Sometimes it is called Pijn means it is depending upon n. If it is not depending upon n, we write it as Pij. And here we can take it as Pij. There is no need of n because homogeneous. Okay. What are the examples of physical systems? These are very important. The state space contain masses, velocities, acceleration of particles, subject to Newton's law. Here we give the different examples. Actually, I gave two examples on one on queuing, another on inventory. These are most common. And Newton's laws of motion. You take the Newton's laws of motion, that is also according to your Markovian property. Future depends only on the present state. So, or a particle will be at rest, or what is Newton's law says, a particle will be at rest or of uniform motion unless an external force acting on it. The external force acting is present. At each instant of time, the external force is acting, it is moving. Therefore, it is a Markovian property. So, previous traction is not needed. And speech recognition, this here also it is a very good application of Markov chain. That is, suppose a person is reading, how the computer will recognize the speech of the person. Suppose the person speaks k words, the k plus 1 word he is going to give, going to spell, that will be automatically catched by this. Okay, by observing the first k words, k plus 1 word can be easily observable. That is Markov. And you look at this epidemic. Now you can take the coronavirus, how it spreads. That is also a same Markov principle, because the future spread of how much people are infected by that depending on the present state. Suppose at present there are 100 people affected by corona, and in future it will be more than 100. It is each 100 has a capacity to spread. Okay, and they may be recovered or hospitalized, whatever it may be. It is then the number of infected is susceptible individual may be modeled as Markov. So this is a very important. So people are modeling this how the coronavirus will spread in future. That is depending upon the Markov chain. Okay, you have this is the very best model. Now let us come to the next part. That is, I told you that is conditional probability is equal to Pij. I call it as Pij. Here I am not mentioning n. Why? Because it is time homogeneous. I am taking this as a time homogeneous. That is, it is from n to n plus 1 or n plus k to n plus k plus 1, whatever it may be, where k equal to anything, and this is same. Or it may be P1, here n in the place of n, will be probability of x2 given x2 is equal to j, given x1 is equal to j. It is also one step probability, that is Pij. What is the meaning of this? This is nothing but the probability of transition from I to j. The system transit from state I to j with one step. The step n to n plus 1. N plus 1 state. Within a one step, the transition taken from I to j, I call this probability is a matrix. I can call it as a matrix Pij. What do you mean by Pij? Pij is a matrix in which, in the corner, suppose there is a finite state space Markov chain. Finite state Markov chain. The Markov chain, I consider the Markov chain xn n equal to 0, 1, 2, 3, which can take the values 0 to m. You can take the value 0 to m. And you take a matrix. Okay. In the column, there are 0 to m. In the row, also 0 to m. Okay. P00 denote the transition from 0 to 0. Probability of transition from 0 to 0. P01 means transition from 0 to 1. P02 means transition from 0. What is the sum of all these for equal to 1? Because starting from 0, the due course, the transition may be taken from 0 to 1 or 2 or 3 to m. Okay, now let us come to this is a matrix. I have not mentioned the matrix here. In future, when problems comes, you will do it. It is a one-step transition probability. Now, what do you mean by two-step transition probabilities? Suppose starting from 0, x0 and x2. x0 is equal to I, at x2 it is two-step probability. If x1 is equal to I, x3 it is day, it is two-step transition. To compute two-step transition probability, it is very simple because you take the square of the matrix. You take the square of the matrix, it will do. This is very interesting property. That is, you take a Pij square, you take the matrix and square it. What happens? That is ordinary matrix multiplication. Sigma k equal to 0 to infinity, Pik, Pkj. It is your probability of, it is multiplication of two matrices, same matrices. And it will give you the answer. That is, I to j, we have to transit from I to j. Instead of going to j, first you take to transition from I to k, from k to j. Then what is the probability of transition from k to j? You multiply these two probabilities, that will give you the probability of transition from I to j. But I to j through k, what are the k? The different states. How many states are there? Infinite states, 0, 1, 2, 3, infinity. You take all these sums, it will give you. Okay, now look at this, how it will work. Pij square is, I can take n plus 1 is k, xn is equal to I, and same thing. It is one step. This is also one step. So we are starting from I am going to k. From the nth state, I am in I and n plus 1 k. And then from n plus 1 in k, I will go to this condition. This is condition. So multiply these two conditional probabilities. That will give you another conditional probability that xn plus 1 will be j, xn plus 2, n plus 2 j, and n plus 1 state will be k. But initially, it will be j. This is why Markov property. Okay, here I am using Markov property. Now, these two, what will be? You take the union of these two sets. Xn is equal to j and it's k, given xn equal to j. That is nothing but xn is equal to j. That will give you two-step transition probability, n to n plus 1. That is your P. Now, let's say, in general, suppose you want to find the n-step transition probability. So, at present, I am in state I, at 0, initially. After n step, I will go to j. Transition. How much the probability is calculated? It is Pijn. And this, how it can be computed? This is, you take the multiplication by n times. You multiply the power of the matrix, P power n. That will do. Now let us come to the another one. What is the P of n plus m? That is P power n into P power n. Okay. So it is mn plus. That means, suppose you want to compute m plus n step probability. First you compute n step probability and m step transition probability. Multiply them in that. This corresponding result is called Chapman-Kolmogorov equation. This will be obtained by this Pij n plus m is equal to, first within n step transition from I to k, then m step it will go to k to j. Totally, this is the sum. Okay, now let us come to the another important thing. How can you find the row vector? After doing, I take a vector Vn. At the nth step, what is the state of the system? At the nth step, what is the state of the system? The first x1 may be in which state? x2 which state? n3 n state. That we can take Vn Vj, possibly infinite row vector of probabilities at time n. That is Van is equal to probability xi is equal to. At the nth step, I will get the state I. What is the probability? At the nth state, in the long run, at the nth state, I will be in state I. What is the probability? So it is a simple probability. There is no conditional probability. In the long run, at the nth state, I will be in I. What is the probability? I call it as a fixed probability, that is Van. If I varies, suppose the state will be I equal to 1, 2, 3, 4, n, and that we can call it as nu. Nu is equal to nu1, nu2, nu3, up to nu n power n, at the n step, Van. What is it? So, nu n is equal to nu 0 into p power n. So, nu 0 is, nu n is what is nothing but bracket, you put a bracket of nu n. But nu n is nothing but, it can be computed by nu 0 into p power n. So your nu I power n is nothing but nu 0 and initially in which state probability, you initial probability vector is there, and into multiply by p power n, it will give you n probability. This is called. In the long run, as n turns to infinity, what happens to the system? We can call it as nu. Nu equal to nu into p. All these n will go. This is called an equation. This is called potential equation. If you solve this equation, nu equal to nu p, you forget all these n, 0 and other things. Nu equal to nu p, it will give you, in the long run, you as n turns to infinity, if this is possible only when the system is ergodic. So I am going to give you what is the ergodic system. And finally, and this is the n-step transition probabilities are computed by nu n is equal to nu 0 into p power n. In the long run, as n turns to infinity, if the system is ergodic, this will converge us to nu equal to nu p, and that is your matrix equation. Now let us come to a very simple problem. The state x0 is equal to 0. Initially, we are at 0 state. And let xn evolves as a Markov chain. You think xn is a Markov chain with the transition probability matrix. This is your transition probability matrix that I told you, that is p is equal to pij. That means this border matrix I can call it as 0, 1, 2. Here also 0, 1, 2. What is 0? P 0, 0. It is 1 by 2. 0 to 0, the transition will take. I can have a transition diagram. Okay. Where 0 to 0, what is the transition probability? It is 1 by 2. From 0 to 1, the transition from 0 to 1 also 1 by 2. But there is no transition from 0 to 2. You cannot go from, that is the probability 0. Next, from 1 to 0, there is no transition. From 1 to 1, there is no transition. 1 to 1, there is no arc is there. Okay. But 1 to 2 is possibility, with probability 1. Definitely it will go to 1 to 2. And here, 2 to 2. 2 to 0. 2 to 0, the probability is 1. And there are other possibilities on 2 to 1, 2 to 0, or 2 to 1 and 2 to 2 are not there. Okay. Now there the probabilities are 0. Now look at this. This is the matrix. Now what is nu 0 n? That is probability that xn is equal to the nth state. It will be 0. That you have to compute by nu 0 power n is equal to find by using probabilistic argument. That you can compute very easily, because n is equal to 0. What is nu n 0? Nu 0 at the n step. It is, you multiply nu 0. Initially the system that you to compute, you cannot compute very easily, because what is the probability that xn is equal to 0 means 0 to 0, or it may go to 0 to 1 and 1 to 0, then it comes to this. Okay, after n step, 3 step. So you put the steps, 1 step, 2 step, 3 step. These all possibilities are, you add all these probabilities, that will give you this. Instead of that, you can do, so you take the initial probability is given, that we can multiply by p power n. That is your formula, it is given here. You apply this, nu n is equal to nu 0. Okay. And you apply this, you will get the result. Okay. Now let us come to the classification of states. The state J is accessible. I can say that from state I, can you go to state J? Then if it is accessible, I call it as Pij power k is greater. In the k step, from I can go from I to j. If it is positive probability, we can say that it is accessible. From I state, I can go to state. What do you mean? Why we need a classification of states? Because I'm going to our purpose is to show that this as n turns to infinity, when the number of trials you take the n means n step transition probability. Suppose in the infinite step as n turns to infinity in the long run, can you say that nu is equal to nu p? This is not possible in other cases, and this is possible only when the states are ergodic. All the states are ergodic. That ergodic means that is that space is recursive We will take a recurrent. The states are recurrent, non-null, aperiodic. If the states are recurrent, non-null, aperiodic, then I can say that it is ergodic. And this property we can hold and we can solve the problems. That is why we need this classification of states to be regarded as, I can divide the states into recurrent states, transient states. There are different kind of properties are there. Recurrent states, transient state, and periodic states, periodic states. Some of the states are periodic states. If all these come together, club together, I can say that it is ergodic. Okay, what do you mean by, I'll go quickly, that is, recurrent means if you start from one state, you can come to the same state recurrent with positive probability. Okay, within a finite number of steps. If you come to the same thing, it is recurrent non-null. Recurrent non-null means starting from I, you can go to different states. Your state space contains so many states, I, J, K, and so on. So starting from the I, can you come back to I? If it is possible, it is called recurrent state. And if you starting from I, you go to some other state, you cannot return to I, then it is called transient. Okay, so that means returning to state I is not possible. It may be possible in the long run, that is infinite, but it will take infinite time. Within a finite time, you cannot reach I. Then that is called transient state. And recurrent, within the recurrent, there are two possibilities. One is recurrent null and recurrent non-null. Recurrent null means, so it will come back to I. Starting from I, you can come back to I, but not within a finite time. Therefore, it is called recurrent null. Starting from I, you can come to I within a finite time, it is recurrent non-null. That means mean recurring time is finite. Okay. And periodic means what? So you can, starting from I, you can come back to the I within a particular period, D. It is fixed within 2 steps or 3 steps or 5 steps. If you are able to come back to the same state within 5 steps, I can say that the period is 5. Each 5 steps, it will come to the same this period. Okay. And if it is not possible, suppose we cannot come within fixed steps, fixed number of time, you are unable to come, it is called aperiodic. Now let us come to do that. I am taking a new concept, that is I to j, is it accessible? The probability is possible. And it can be represented by the finite graph. Okay, 0 to I, 0 to 1 is possible, 1 to 2 is possible, transient, but 0 to coming back, 4 to 2 is not possible. So 4 is accessible from 0, but not vice versa. When I and j are communicate, how can you say that communicate means you can access I from j, we can access j from I, then it is double arrow, I to j, I call it as communicate. And this is nothing but a equivalence relation on the state space. Okay, the equivalence relation means what is the reflexivity, symmetric property, and transitivity. Both properties, these 3 properties are automatically true. Okay, I is accessible from I. I can communicate with I. I to j communicate means j to I also communicate. And all these things. Therefore, we know that if there is a equivalence relation on a set, automatically it will divide into so many equivalence classes, and we can call it as communication classes. So when this Markov chain is irreducible means its state space is only one communication class. There is no different classes. If it is divided into so many communication classes, from one class to another class, the communication is not possible. If it is irreducible means it can communicate within the state. Communication is very easy. Okay, all states are communicable. The communication class contain I. It is absorbing. What do you mean by absorbing state? So some of the state, it is I is an absorbing state. If you go to that state, you cannot return. Okay, you have to observe that. For example, there are some states 0, 1, 2, 3, 4. If you go to 4, you cannot return. Okay, then it is observing state. If you go to 0, you cannot return. These 2 ends are observing states. There are some states of reflection state. If you go to 4, you can immediately come back to 3. That is called reflecting state. Okay, reflecting state. And these are the things that, an observing class can be left there. So communication class and all these things you do. So that all states in the same communication class have the same period. So what do you mean by period? I will tell you. The state I has period D. If Pi by n is equal to 0 and n is not a multiple of D, and D is the greatest integer, this is the greatest common divisor, and such that it can be returned to the same state, I can say that it is a period. The I is a state with period D. And D is equal to 1. Suppose D is equal to 1, the greatest common divisor is 1, means all these steps are not uniform. It is the steps are not multiples of a particular number. 5, 10. Only this is multiple of 5. The greatest common divisor is 5. But if it does not occur, then it is D is equal to 1. Greatest common divisor is 1. That is a period. So you take this. Period means what? It will go to I plus 1, I plus 2. At D minus 1 step, it will come to this. That means the period is D. Now, how can you say that I is recurrent? Re-entering I, starting with I, it is re-enter is equal, I is equal to 1. The probability of re-entering is 1. It is called recurrent. If it is not recurrent, then it is transient. So it is given here. So all these things are, then I can mean recurrent time. I call it as mu II is equal to mean expected return time. Expected return time. If the expected return time is finite, it is recurrent. Recurrent, non-null. If mu I is equal to infinite, it is recurrent, non-null. So all these probabilities, you can do this. NIFT means number of renewal. Each time you will come to I. So I is a specific point. If you come to I again and again, it is a renewal process. And this renewal counting is given divided by T and given by mu. Okay, this is a very important theorem. Y is recurrent if and only if sigma I equal to Pii by n is equal to infinite. Recurrent means that is probability of returning to state I is positive. So each time it is positive probability, you add all this positive, it is always infinite. Okay, suppose it is recurrent is 0, if the sum of the 0, it is not infinite, it is finite, and then it is, we can call it as transient. So that if I is recurrent, I and they are communicable, then they is also recurrent. Another theorem is if I is transient, what is mu I? Returning time is infinite. If I is recurrent, the returning mu I is mean recurrent time is infinite, finite. Then I is said to be positive recurrent. If it is so, it is called positive recurrent. If mu I is equal to then it is null recurrent. So sometimes it is called positive recurrence and null recurrent. Null means it is positive, or positive recurrent or null recurrent. If I is recurrent, then I and A both positive recurrent and both communicate. Okay, that one theorem is missing. That is, if there is a state I which is positive recurrent, aperiodic, not periodic, positive recurrent, aperiodic, then we can call it is ergodic. That I will mention later. That theorem is later. So I am going to close this session because it is almost time. Okay, and positive, you should remember that it is positive recurrent and aperiodic. It should not be periodic. Then it is, this state is called ergodic. If the state is ergodic, if all the states are ergodic, if one of the state is ergodic, the class elements all are, if it is irreducible, if Markov chain is irreducible, we can call it all the states are having the same property. That is, all are periodic, all are positive recurrent. Therefore, it is an ergodic. In the ergodic case, you will get nu equal to nu p, that equation. So you take a simple random walk. Okay, it's a Markov chain on integers that I told you. A person starting from, you take our integer set on the real line, you take 0, 1, 2, 3 on the left side. On the right side and left side, it is minus 1, 1. A drunkard man is walking from 0 to, he will go to 0 to 1 with probability P. and he may go to from 1 to 0 with the probability 1 minus p. Okay, this is given here. Xn plus 1, xn plus 1 step is equal to xn plus 1, that is 0 to 1 or 1 to 2. This will occur with the probability p, or xn plus 1 equal to xn minus 1. Go back. A drunkard person will actually go one step forward and one step backward, or sometimes 2 steps backward and 1 step forward. And this is the probability. You count it as the probability of forward and probability of backward. And this is nothing but a random walk. And this is a good example for your Markov chain. Symmetric random walk, all these things are there. And what do you mean by stationary distribution? A distribution is said to be stationary if pi I, it is state, it's a probability that, what do you mean by pi I? Pi I is the probability that the system is in state I in the long run for I equal to 0, 1, 2, 3. If I equal to 0, pi 0, pi 1, pi 2, pi 3. This pi is a stationary distribution. If P is equal to, you get a transition probability matrix such that pi j is equal to pi I pj. This is why I call it pi equal to pi p. Are you able to understand pi? So this is why I call it as nu equal to nu p. Here I think because it is a stationary distribution, in long run it becomes limiting distribution and it is an irreducible aperiodic positive. I told you that is, this is called ergodic. Markov chain have a unique stationary distribution which is also the limiting distribution. So I call it, just you solve this equation. If you know the P, transition probability matrix, and the initial conditions, and finally you solve this pi equal to pi p equation, and you will get a steady state probability for each state. And this problem, using this you can solve so many problems. But what is pi j? At its limit entrance infinity pij. In the long run, as entrance infinity, what is pij? That will become a steady state. And such Markov chain is called ergodic. Okay. So if you do pi power n as entrance infinity, you take n times pij matrix, multiply it by n times, you will get a matrix. Put n times infinity, automatically all the rows. If you take pij, initially the probabilities may be different. The first it may be 0.5, 0.3 or something, and second row it is 0.3, 0.75 and so on and so on. But as you take n times, multiply by n times, and as n turns infinity, all the rows are equal, same. You get 0.2, 0.3 and 0.1, total is 1. And second row also same 0.2, 0.3 and same thing occurs, and that is called your steady state probability pi j. Very clear? If it is true. And with this, we can solve so many problems. That is, you solve this equation, pi equal to pi p, you will get a unique stationary distribution solutions. And with this, I complete my lecture. Okay, if you have any doubt, you can ask. And this is the last 5 minutes.
Sir, I think no any questions, sir.
Okay, thank you. If there is no question, I can stop
Thank
here.
you, sir.
Okay, thank you. Thank you very much.
Thank you. Thank you so much, sir.
Okay, thank you.
On behalf of PG and Research Department of Mathematics, thank you for spending your valuable time in our C4 session, sir. Really, it's a wonderful session to all our students and CSIR aspirants. I would like to thank Professor R. Venkatramanan, Head PG and Research Department of Mathematics, for organizing this C4 workshop. I am very proud to inform about our next webinar titled An Introduction to Queuing System. Resource person, Dr. Anup N. Nair, Assistant Professor and Head, Department of Mathematics, College of Engineering and Management, Alappuzha. Our next C4 session will be held on tomorrow at 11 a.m. Thank you.